In this session, we're going to talk about whole numbers and the base 10 system. So the whole numbers consist of 0, 1, 2, 3, and so forth. The counting numbers start with 1, 2, 3, and if you ask a little kid to count, they're not going to start at 0. But when we add 0 to that set, we get the whole numbers. So in set notation, this could be written as the whole numbers, or the set, so you read this, the set, of 0, 1, 2, 3, etc. So especially when you're talking with younger kids, you can think of the whole number as the possible answer to how many cookies are on this table. And the table doesn't have to have any certain size. Well, unfortunately, right now, on my table, there are 0 cookies. But there could be 1, 2, 3, there could be 1,000 cookies on the table. Okay, but there are no parts of cookies, only whole cookies. So we don't have 1.5, 2.37, or whatever. So when we talk about different sets of numbers, we talk about properties that go with those sets of numbers. And these properties will extend to other sets that we'll talk about. But specifically for the whole numbers, we have the reflexive property, which says any number is equal to itself. That may seem really self-evident, but in mathematics, we make sure we set down the rules so later on we can derive more rules from them. Then we have the symmetric property. If I have A equals B, then B has to be equal to A. Again, that almost seems like it's self-explanatory. So if I have that 4 is equal to X, or if I have 12 is equal to Y, then, and this property has an if part and a then part. So if 12 is equal to Y, then I can say Y is equal to 12. Finally, we have the transitive property. And you can kind of think of this as translating something. So, suppose I can speak 2 languages. So I can say something in English and then say the same thing in French. Then I know the French and I can translate it into Japanese. Because I know all those things, I could say the English statement in the Japanese form. Okay, so kind of looks like this. If A is equal to B, then I know that B is equal to some other number C. If those two are true, then A has to be able to equal C. So if I know X is 5 and 5 is Y, then I know X is equal to Y. And again, these seem almost self-explanatory, but as we set down these rules, we'll be able to use them to derive more properties. Now, the number system which we use is a Hindu-Arabic system. And it's called that because it was named for the Hindus who invented it. It was their notation and their ideas. And then the Arabs were the ones to transmit it to Europe. So this is a base 10 numeration system in which the place value is determined by the position of these digits. So we have the digits 0 through 9, okay? And then once we get to 9, we start regrouping. and we go to the next place, the tens place, and then we go to the hundreds place after we get 10 of those together. So the base tells you what you're going to group by. So because it's positional numeration system, where the number is, its position tells you the name of it and the value it has in that position. So these are some of the place names in our base system, starting with when we have a whole number, and you all are familiar with decimal numbers, so a decimal would go right here at the end of a whole number. But we have ones, tens, hundreds, thousands, 10,000s, 100,000s, and so forth. Now, the base 10 tells us that's what we regroup. When we start regrouping, we regroup when we regroup when we reach that number. So if we have 10 ones, it goes into the tens. If we have 10 tens, it goes into the hundreds. So each of these is a multiple of 10 of the place before it. Now, notice in this picture, I'm going to point this out, that we have this purple set, and this yellow set, and this pink set. So they're grouped in these sets of threes, which is called the period. So in English, the number names for whole numbers from 1 to 20 are all single words. From 21 to 99, except for the multiples of 10, they have compound number names that are hyphenated. And so 23, again, my pen just went kind of nuts. Okay. Even if this was in the 10,000s place, 23,000th, then you would still hyphenate it in that place when you spell it out. So if I want this number, 347, we start with the biggest place, 347. Notice there's no and. We don't read an and in the whole number. So when we get past 999, then we go to the thousands place. So each time we get past a 3-digit number, we go up, and then we'll have a new period. It's what it's called, that group. So that is our thousand. Then we have million. Then we have billion. Then we have trillion, and so forth. So when you read the number, you read what the 3-digit number would be and its period name. And you read that as you go through the whole number. So this is 23 trillion 478 billion 506 million 42,319. Notice we do not use the word and. Even though we commonly say 319, someone may say, really the number should be read 319. Because the and indicates a number that has a decimal portion. Now, if I look at the digits, okay, I have 75,063. So 7 is in the 10,000s, 5 is in the thousands, 0 is in the hundreds, 6 is in the tens, 3 is in the ones. So I used that place name to write this number in expanded form. So the 7 times 10,000, that would be this place. 5 times 1,000, 5,000. No hundreds, so I have 0. 60, 3. So the expanded form of a number is the sum, here's the sum, of each number times its place value position. Base 10 blocks can kind of help us visualize the base 10 numeral system. So we start out with a block we call a unit. And since we regroup at 10, we take 10 of those and we form a new measurement. And then we take 10 of those together and we form a new measurement. So it looks kind of like this. I start out with the ones, and these are usually called small cubes. And then when I put 10 of those together, I get what's called a long. And then when I put 10 of those together, I get each of these, which is commonly called a flat. And then if I put 10 of these and stack them up on top of each other, I get the cube, the large cube. So we have 4 sizes when we use base 10 blocks. It is not that we can't go beyond that base, but we don't have a way to physically, beyond these blocks, but we don't have a way to physically represent that. Okay, so again, this is our unit cube, or small cube. We put 10s together, call it a long, or you can call it a rod. Put 10 of these together, and you get one of these. Represents 100, because if you put 10 tens together, you get 100. And this is called a flat. And then when you put 10 flats on top of each other, you get this large cube, which would have 1,000 cubes in it, because 10 times 100 is 1,000. So I can use these base 10 blocks to represent numbers, and I use the place names with the size blocks it is. So I have these 2 large cubes, which are the thousands. So I have 2,000. I have 3 of the flats, which are hundreds. And I have 1, 2, 3, 4, 5, 6 of the longs. So that's 60, or 6 tens. And then I have 1, 2, 3, 4, 5, 6, 7 ones. So to write this number, it's 2,367. If you watched the basic skills test videos, I discussed rounding in them. Okay. But we're going to talk about rounding whole numbers here. So when you round a number, you want it to be reasonably close to the number you started with. So if I have a number like 391, and I want to round it to the nearest hundred, I go to the hundreds place, and then I look immediately below it. If this number is 5 or greater, then this will go up. So 391 rounds to 400. Now I have had people say, okay, I'm taking 391, I know I need to round this up to a 4, but forget to put the zeros. So what they're telling me is that 371, and we use this for approximately, is approximately 4. But if you went to the bank and you had $391 and they told you that there was only $4 there because they rounded it up, wouldn't you be upset? I know I would be, right? It's the difference between being able to buy a candy bar and being able to buy something much larger. If the digit next to it is between 0 and 4, then I leave the place value the same. So 391 rounded to the nearest 10. So I go to the tens values. I look immediately to the right. There's a 1 there. So since it is 4 or less, then I just leave the 9 the same and then place my 0. The other thing with whole numbers that is very important for students to start getting the idea of is a number line. And that number line, as they go into other kinds of numbers, like fractions and decimals, will help them understand it better. So we have these intervals, and then we mark them off at the same distance from each other, and we use each of those intervals to represent a whole number. So here's a whole number line. Okay. Now the whole numbers start at 0, so we just put the arrow on this side, but we're not considering any of those numbers down here. But the number line goes on and on forever in the negative and positive directions. But we're only plotting, like I said, whole numbers, so we start with 0. Okay, so these tick marks tell us where each interval is. Okay, and it has to be in increasing order. Okay, so you make the tick marks and then you label them, but they have to be labeled in increasing order. Sometimes when students start out, because I think this is why, when we write out a number, the furthest left is the largest place, but on the number line that's not the case. The number line says it has to go in increasing order. And it's that tells me which number is bigger than another. So one number is larger than another number if it is to the right of it. So 4 is larger than 3. Or we can use the greater than symbol, because 4 is further right on the number line. Or I would know that 2 is less than 5 because 2 is further to the left on the number line.